Think about how we usually learn science, memorizing formulas from textbooks, staring at equations on whiteboards, and running experiments in sterile modern laboratories. Observe this dark indigo dye, violating its surface tension as it splashes and bubbles inside a stone vat. These artisans are managing complex chemical reactions in a workspace optimized for fluid control. The problem with typical science education is the abstraction barrier. When we strip natural laws away from the vibrant world and trap them on paper, they start to feel like artificial rules instead of the actual forces governing reality. We lose the connection between the math on the page and the materials in our hands. To bridge this gap, educators are looking at the intersection of heritage and STEM, using traditional crafts like batik as practical case studies for physics and chemistry. By tracking the creation of a single piece of traditional batik, we can see exactly how artisans mastered thermodynamics, colloidal chemistry, and applied geometry centuries before modern schools existed. The process begins with a plain white cotton cloth called mori. But raw cotton is naturally coated in starches that act as a barrier, preventing the fabric from absorbing any dye. To remove that barrier, artisans use a technique called ngetel. They soak the fabric in a precise mixture of peanut oil and ash soda. Under a microscope, this water and oil emulsion acts. Molecules of peanut oil and ash soda surround and extract starchy particles, pulling them from the cellulose fibers. This clears the microscopic pores, leaving them wide open to receive dye. This soaking stage prepares the fabric at a molecular level, clearing the path for permanent dye bonds. Next, the artisan applies a hot mixture of paraffin and beeswax, using a specialized copper tool called a canteen. Applying the wax forces the artisan to manage heat transfer and flue resistance in real time. If the temperature of the wax drops, it becomes too thick to flow and will eventually crack on the surface. But if it gets too hot, the wax will thin out and burn straight through the delicate cotton threads. Using a traditional angle furnace, the artisan maintains a constant temperature. This allows the liquid wax to seep precisely into the fabric's microscopic pores. The artisan's hand acts as a manual valve, balancing heat and viscosity to create a waterproof physical barrier. These complex motifs, like the kangkung setingkes pattern seen here, are the hallmark of batik. These intricate patterns rely on a foundation of rigorous mathematical logic. Beneath the floral designs lies a technical grid mapping the layout, points, lines, and intersecting angles. Artisans expand this using 4 geometric transformations: sliding shapes in a translation, spinning through rotation, mirroring for reflection, and scaling via dilation. These designs are perfect executions of advanced applied geometry, drafted entirely without modern measuring tools. With the wax barrier set, the fabric is dyed. Natural plant dyes act as colloidal sols, solid particles suspended in liquid, that bond with the exposed cellulose fibers. In a final step called pelarodin, the cloth is plunged into boiling water to melt and strip away the wax. The wash uses soap from the Lerak fruit. It creates a colloidal aerosol that cleans the fabric without breaking the dye bonds or polluting the water supply. This is a sustainable chemical cycle, perfected long before the modern concept of green chemistry was ever defined. The finished piece of batik is more than a textile. It is a physical record of the sciences. This cloth is the result of specific molecular bonds, the charted heat transfer of the wax, and the precise geometric lines mapped across its surface. Grounding science in heritage removes the disconnect between theory and practice, allowing students to touch and manipulate physics in the real world. Indigenous wisdom and modern STEM are simply different languages used to describe the exact same universal law.